Welcome dear student in lecture 3. In the last lecture we have studied various psychometric properties, and in this lecture we will cover remaining psychometric properties, which are enthalpy of moist air, adiabatic saturation temperature. Apart from that, we will do some numerical problem also. Let's take the enthalpy of moist air first. As we already discussed in the previous lectures, moist air is not a pure substance. So we cannot find the value of its enthalpy directly, like in case of steam or other refrigerants. So we have to calculate it with the help of dry air and water vapor. According to the Gibbs law, the enthalpy of a mixture of perfect gases is obtained by the summation of the enthalpies of the constituents. We know moist air is the mixture of dry air and water vapor, and both can be treated as ideal gas. So according to the Gibbs law, the enthalpy of the moist air is the summation of the dry air part and water vapor part. Therefore, the enthalpy of moist air can be written as H is equal to MA HA plus MV HV, where H is the total enthalpy of moist air, and MA is the mass of dry air, and HA is the enthalpy of dry air, and MV is the mass of water vapor present in the moist air, and HV is the enthalpy of moist air. Notice that this is the total enthalpy, and we have to calculate the value of specific enthalpy. The specific enthalpy of moist air is always calculated per unit of dry air instead of moist air, because the mass of water vapor kept on changing in the moist air. So the specific enthalpy of moist air per unit of dry air can be written like this. So that is specific enthalpy of moist air per unit of dry air equals to HA. So we divide this equation by MA. So we have specific enthalpy of moist air equals to HA plus MV by MA. So MV by MA is the specific humidity, omega. So we have omega HV. So H is the enthalpy of moist air, kilojoule per kg of dry air, and HA is the enthalpy of dry air part, and omega HV is the enthalpy of water vapor part or moisture part. Taking 0 degree centigrade as the reference temperature, the enthalpy of dry air can be determined from equation HA is equal to CPA multiplied by TdB, where HA is the specific enthalpy of dry air part, and CPA is the specific heat of dry air at constant pressure, and TdB is a dry bulb temperature. Remember that the dry bulb temperature always in degree centigrade in this equation. For the air conditioning application, the value of CPA can be taken as common. So if we put the value of CPA, our equation becomes this. So enthalpy of dry air part is HA is equal to 1.005 multiplied by dry bulb temperature. Again, taking 0 degree centigrade as reference temperature, the enthalpy of water vapor can be written as 2500 plus CPV multiplied by dry bulb temperature, where CPV is the specific heat of water vapor at constant pressure. The enthalpy of the water vapor at 0 degree centigrade is 2500 kilojoule per kg. So enthalpy of water vapor is 2500 plus CPV TdB. The value of CPV can be taken as 1.88. So our equation becomes 2500 plus 1.88 into dry bulb temperature. As we know, enthalpy of the moist air is the summation of dry air part and moist air part. So our equation will be H is equal to HA plus omega HV. So the enthalpy of the moist air is H is equal to HA plus omega HV. So we can write HA as 1.005 into dry bulb temperature plus omega, and HV can be written as 2500 plus 1.88 into dry bulb temperature. So we can calculate the enthalpy of the moist air if we have the value of dry bulb temperature and specific humidity. The next property is adiabatic saturation temperature. Consider a system consists of a long insulated channel that contain a pool of water. A steady stream of unsaturated air that has a specific humidity omega 1 and temperature T1 is passed through this channel. So we are considering a system with long channel which is adiabatic or insulated, and this channel contain pool of water. A steady stream of unsaturated air enter to this system, and a saturated air is leaving this system, where T1 is the temperature of this unsaturated air which is entering into the system, and omega 1 is the specific humidity and phi 1 is the relative humidity. When air passes through this system, some water vapor from the pool evaporate and the moisture content will increase. So at the exit we have saturated air. So this saturated air at temperature T2, and the specific humidity of this air is omega 2, which is omega s, and relative humidity phi 2, which must be equal to 100%. Let us assume that m dot A1 is the mass of dry air that is entering into the system, and m dot A2 is the mass of the dry air which is leaving to the system. Notice that we are talking about only the mass of dry air. As some water is evaporate from this pool, so the makeup water with the rate of m dot F is supplied to this pool to maintain the level of the liquid. As the air flow over the water, some water evaporates and mix with the air stream. So I have already discussed this. The moisture content of the air increase during this process. So as water evaporates and mix with air, it is obvious moisture content will increase. So moisture content will increase in this process and its temperature decrease, since the part of the latent heat of vaporization of water that evaporates come from the air. So this is very important point, and I will discuss this point in the upcoming lectures in the topic of evaporative cooling. For the time being, you have to remember that when the moisture content of the air is increased, its temperature is decreased. If the channel is long enough, the air stream exits as saturated air, 100% relative humidity at temperature T2. So the temperature of this saturated air is known as adiabatic saturation temperature. If makeup water is supplied to the channel at the rate of evaporation at temperature T2, the adiabatic saturation process, which is described above, can be analyzed as steady flow process. So we can analyze this process by considering the steady flow. So there is no accumulation of mass or energy. Apart from that, we have to remember that the makeup water which is supplied to the system is equal to the rate of evaporation. So the rate of evaporation of the water and the rate of feed water are same. So first apply the mass balance. As we know, moist air has two parts, dry air and water vapor. So we apply the mass balance separately. So first for the dry air part. M dot A1 is the mass of dry air entered into the system, and m dot A2 is the mass of the dry air exit from the system. So there is no accumulation of mass, so m dot A1 is equal to m dot A2, which we can say m dot A. Now apply the mass balance for the moisture part. If m dot V1 is the mass of water vapor present in the air enter into the system, and m dot F is the mass of water vapor that is evaporate in the long insulated channel, which is equal to the supplied makeup water m dot F, and m dot V2 is the mass of water vapor in the exit air. So from the mass balance we know that m dot V1 plus m dot F must be equal to m dot V2, because there is no accumulation of mass in the steady flow. So this is for the mass of water vapor. We can write this m dot V1 in terms of omega 1. So m dot V1 can be written as omega 1 m dot A. Omega 1 is the specific humidity of the air which is entering into the system. So that is, so omega is mass of water vapor upon mass of dry air. So we can write m dot V1 equals to omega 1 m dot A plus m dot F equals to omega 2 m dot A. Now simplify this, we will get m dot F is equal to m dot A omega 2 minus omega 1. So we have the value of m dot F in terms of Ma. Remember that this m dot F is the mass of water which is supplied at temperature T2. Now apply the energy balance. Since it is a steady flow process, so energy enter is equal to the energy out. Can be given as m dot A H1 plus m dot F HF2 equals to m dot A H2, where H1 is the enthalpy of the moist air which is entering into the system, and H2 is the enthalpy of the air which is leaving the system. So this is the enthalpy at temperature T1 and this is the enthalpy at temperature T2. This mf mass of water is supplied at temperature T2. So this is the enthalpy of the liquid at temperature T2. Now put the value of m dot f, which is in terms of m dot a. So now put the value and we will get this equation. So in this equation we are clear that m dot a will be cancelled out. So after cancelling the m dot a, we will have h1 plus omega 2 minus omega 1 multiplied by hf2 equals to h2, where h1 is the enthalpy of moist air at temperature T1 and h2 is the enthalpy of moist air at temperature T2, and hf2 is the enthalpy of water at temperature T2, and omega 2 and omega 1 are the specific humidity. We also know that the enthalpy of the air is the summation of enthalpy of dry air and moist air part. So we can write this h1 and h2 like this: Cp T1, where T1 is the dry bulb temperature. T1 is the dry bulb temperature. So Cp dot T1 plus omega 1 HV1 plus omega 2 minus omega 1 HF2 equals to Cp T2 plus omega 2 HV2. So by simplifying this equation, we will get omega 1 multiply HV1 minus HF2 equals to Cp T2 minus T1 plus omega 2 HV2 minus HF2. So we have this equation. So HV2 is the enthalpy of saturated vapor at temperature T2, and this HF2 is the enthalpy of saturated water at temperature T2. So we can write omega 1 HV1 minus HF2 equals to Cp T2 minus T1, which is remaining same in the previous equation, plus omega 2 dot HFG2. So this is the latent heat. HV2 minus HF2. So this is the latent heat at temperature T2. So by simplifying that, we can find out the value of omega 1. So this is the relation from where we can find the value of omega 1, and the omega 2 can be calculated from this equation. So these two equations very helpful to solve the numericals. Now let's take a numerical problem. So problem is a room 5 into 5 into 3 meter cube. So this is the volume of the room. So our room contains air at 25 degrees centigrade and 100 kilopascal at a relative humidity of 75%. Determine the partial pressure of dry air, the specific humidity, the enthalpy per unit mass of dry air, and the mass of dry air and water vapor in the room. We have given the volume of the room, which is 5 into 5 into 3, which is 75 meter cube. Dry bulb temperature 25 degrees centigrade. So this is the room temperature. So it is the ordinary temperature, and dry bulb temperature is the ordinary temperature. So dry bulb temperature is 25 degrees centigrade, and the total pressure 100 kilopascal, which is the summation of partial pressure of dry air plus partial pressure of moist air, and the relative humidity, which is 5 equals to 75%. And we have to calculate the partial pressure of dry air, specific humidity, enthalpy, and the mass of dry air and water vapor in the moist air. So first we have to calculate the partial pressure of dry air. We know the total pressure P is equal to the partial pressure of dry air plus partial pressure of water vapor, and we have the value of total pressure 100 kilopascal. So if we have the value of PV, partial pressure of water vapor, then we can find the value of PA. So let's understand this problem with the help of TS diagram. So initially we have a moist air in which the moisture content is here in the. So to calculate this pressure, we require this temperature, but the dew point temperature is not given. So what we can do, we can calculate the value of PS. So PS is the saturation pressure at temperature TBD. So we have a dry bulb temperature which is 25 degrees centigrade, and this temperature we can calculate the value of PS when the air is saturated. So from there we can calculate the value of PS. So the value of PS can be calculated from the stream table. So let's see the stream table. So there is a temperature, this is the absolute pressure. So our temperature is 25 degrees centigrade, and so against the 25 degrees centigrade our pressure is 0.0317 bar. So this is our value. So now put this value. So PS is equal to 0.0317 bar. Now convert this into the kilopascal. So we will get 3.17 kilopascal. We know that this relative humidity can be defined as the partial pressure of water vapor divided by the partial pressure of the saturated air at the same temperature. So we have the value of relative humidity and the partial pressure of the saturated air. So we can find out the value of PV. So now put the value. We will get the value of PV is equal to 2.38 kilopascal. Now put this value into this equation. So we will get the partial pressure of dry air is 97.62 kilopascal. So we have calculated the partial pressure of dry air. Now we are going to calculate the specific humidity. Specific humidity is equal to the 0.622 PV by PA. So we have the value of PV and we have the value of PA. So we can calculate the value of specific humidity, which is equal to 0.0152. And the unit is kg of water vapor divided by kg of dry air. Now we have to calculate the enthalpy. So enthalpy of the moist air is equal to the HA plus omega H, where HA is the enthalpy of dry air and HB is the enthalpy of moist air. So H is equal to 1.005 multiplied by dry bulb temperature plus omega 2500 plus 1.88 into dry bulb temperature. So now put the value. Dry bulb temperature is 25 degrees centigrade. By putting the value, we will get the enthalpy is equal to 63.8394 kilojoule per kg of dry air. Remember that the enthalpy of the moist air is always calculated with respect to dry air. Now the mass of dry air and mass of water vapor are remaining. So both the dry air and water vapor fill in the entire room completely at room temperature. So the temperature of the dry air and water vapor will be same and they will occupy the same volume. Apart from that, we are also considering both as an ideal gas. So we can apply the ideal gas equation to calculate the mass. So the mass of water vapor is partial pressure of water vapor into volume divided by gas constant for water vapor into temperature. If we put the value, we will get 85.61 kg, and similarly we can calculate the mass of dry air. So if you have any problem in this numerical, you can ask me. That is all for this present lecture. More numerical problems will be taken in the next lecture.